Hello, I welcome you all to your own channel MSK Learning. In this video, we will discuss the derivation of a stiffness matrix for one-dimensional heat conduction element. So for that, we will take one bar element like this of having length is L, right, which is having two nodes. At the node 1, the temperature is T1. This is the node 1, right, here, and the node 2, right. So at the node 1 the temperature will be T1 and the node 2 the temperature is T2, right. So this length is in x direction. Now for a stiffness matrix for that for heat conduction element, we have a that is a stiffness matrix. You know, in your two-dimensional body, that stiffness matrix general equation is what? That K is equal to, it's better we will write down the KE. Stiffness matrix is equal to integration of B transpose, right, into D into B into dV, right, where the B is a strain displacement matrix. B is a strain displacement matrix, all right, and D is a strain material properties matrix or material properties matrix, right, and dV is the change in volume, all right. Now then also, you know, the temperature distribution function in a heat conduction element, that T is equal to N1 T, that is T is equal to N1 T1 plus N2 T2, right, where N1 and N2 are the shape functions. We can say N1 and N2 are shape function, right, and this N1 is equal to L minus X upon L, and N2 is equal to X by L, right. So that we already know in your previous video, that what is the N1 and N2, how we derive. Now what we need to do, that we have to strain displacement matrix means what? This shape function we need to differentiate with respect to X to get the B, right. So B is equal to, you can say that a strain displacement matrix B is equal to dN1 by dx comma dN2 by dx, right. It means this is the strain displacement matrix. So dN1 by dx means what? This is a shape function at node 1, we have to differentiate with respect to the x, and shape function node 2 you have to differentiate with respect to the x. So when I say dN1 by dx is equal to what? Let's differentiate. So minus x differentiation is minus 1, so it will be minus 1 by L, and dN2 by dx is equal to what? X differentiation is also 1, so it is 1 by L. Okay, now so B is equal to what now? So B, strain displacement matrix B is equal to, you have minus 1 by L comma 1 by L, all right, and B transpose is what? That B transpose is equal to minus 1 by L, and this is the 1 by L, this value we got. Now we need to find that B means, if you look at that stiffness matrix equation, that B transpose dB into dV. So B we already got, that is minus 1 by L and 1 by L. Transpose means what? The row is column converted into column, and column is converted into row. D is what? D is a strain displacement material properties, right. So here we go, that D is equal to, we can say K, right, that is matrix of K, and this is equal to K, is what? Is equal to thermal conductivity of material, thermal conductivity of material, right? So whatever the bar element we have selected right now, so that bar is made up of certain material. So that material is having thermal properties, and that thermal properties we call it as a thermal conductivities, right? That is the K, right? So now you have a K is equal to what, you know, that is integration of B transpose, again we are writing that equation, into D, right, into B into dV, right? So now this that whatever the bar element you have chosen, that bar element length is varying from 0 to L, right? So we need to integrate this function, that is from 0 to L, and B transpose is equal to what? B transpose we got, that is minus 1 by L and 1 by L, right? And D is equal to what we can write, that this is a stiffness matrix K. D is equal to K, you can say thermal conductivity, right? This is a stiffness matrix K suffix E, and this is the thermal conductivity. And B is equal to what? B is equal to minus 1 by L comma 1 by L, right? And dV is equal to what? dV is equal to that A into dx, that is area into length. All right, now further you can say this A and K we can get common. All right, so when we get A and K common, so this equation will be like this, that is AK integration from 0 to L, and this matrix and this matrix will be simplified. So what you need to do, 1 by L into 1 by L, that is 1 by Ls square, right? And again this will be multiplied this one, that is minus 1 by L, and 1 by L, that is minus 1 by L. So it will be 2:2 matrix will come, that is like this, 1 by Ls square, this into this, right? Again this into this, so it will come here right now. So it is what? Minus 1 by Ls square, right? Further this into this, that is minus 1 by Ls square, and this 1 by L into 1 by L, that is 1 by Ls square. This is your simplification, this row into this, that is 2:2 matrix will get into dx, right? Now so this is also means we are differentiating with respect to the, integrating with respect to the dx, right? So this also we can take it out, right? So its integration is what? Its integration, dx integration is x. When we put the limit, that is L minus 0, so it is L. So you can write like this, AK into 1 by Ls square minus 1 by Ls square minus 1 by Ls square, and this is 1 by Ls square, right? And integration from 0 to L, this is the dx, right? So now this is what you have, a AK dx is x, so we have like this, 1 by Ls square minus 1 by Ls square and minus 1 by Ls square, this is 1 by Ls square, right? Dx integration is x, so we'll put the limit, that is L minus 0. This is what simplification. So Ls square, 1 by Ls square, we can, Ls square will get common, so it will become, that is AK L by, this is what we have, a Ls square. So here we have 1 minus 1 minus 1, sorry, that L square I am getting common, so this equation will be AK into L, right, and by Ls square. So this is 1 minus 1, 1 minus 1 minus 1 and 1. So 1L get cancelled. So this is stiffness matrix KE is equal to AK by L, 1 minus 1 minus 1 and 1. So this is the stiffness matrix for heat conduction problem for one dimensional bar element, right? So here A is the cross sectional area, K is the thermal conductivity of the material, and L is the length of the element. So this is how we will derive the relation for stiffness matrix for one dimensional heat conduction problem. Thank you.